All right, so we're going to get started on section 4.3, and in this section, we're going to be talking about different representations of integers to a given base. We are all familiar with what we call the decimal number system. The decimal number system is an example of what is called a positional number system. Okay. Positional system. In the decimal number system, which is an example of this, we use the digits zero, 1, 2, up to 9, and we represent a number, all right, usually in this form. Let's look at an example: 3, 4, 5, 6, 7, 8, and these digits, they have different values, as you know, depending on where they appear, all right? So this is the units, tens, hundreds, and so on. Now, of course, there are many other types of number systems that they are also what we call positional number system. They just use different digits. So before we get farther in this, well, we know what's the meaning of this. Means this number, actually from here on, we're going to be denoting numbers like sub 10. Okay, if there is any confusion of what type of, that's positional number system we're using or base we are using. So this one is, let's see, this is 10 to the power 0. We think of this as 10 to the power 1, 10 the square in here, 10 to the third, 10 to the fourth, and 10 to the fifth. So this one, the numerical value of it, where the 3 here, it actually worth 3 times 10 to the fifth, and then the 4, it is 10 to the fourth, and so on. 5, 10 to the third, 6, we have 10 to the square, and 7 10 to the first, and this is 8 10 to the 0, which is just 1, but that's what it is. All right. Of course, there are other types of positional number system. They are used, especially in computer science. For example, we use what is called the binary system, or we call this is another name for we call it base 2 system. So the decimal system, we call it also, we call this is actually base 10 system. And in the binary system, we use actually 2 digits, all right, 0 and 1. And we're going to show today that is any integer can be actually represented using any base, which is a given number, b, bigger than 1, all right? And by using digits from 0, 1, 2, and so on up to b minus 1. Sometimes even in some of the number systems that we will be mentioning in here, use some letters, okay? Actually, the digits, all right, they could be anything, all right? Since we get used to, the ordinary, these are the Arabic digits, then that's what we use. All right. Other one is in common use is octal. You see how this one is octal system. or this is called base 8 system. And of course, use the digits of 0, 1, 2, up to 7. And then we have the hexadecimal system. And this is base 16. All right, system another way. Say this, and this one is using all the digits that we are familiar with tonight. They're using A, B, C, D, E, F. There is a total of 16 of these. We are not really very much interested in, converting between these different systems. Means given a number in a decimal, how to convert it to a binary, system, or to an octal system, and vice versa, or doing arithmetic with these. More or less, we're going to just look at this possibility that we can actually use any one of these systems. So the main objectives of this section, basically there's a couple of objectives, is number one, to show that any integer can be written or can be expressed or expanded using any base, which is any given number be bigger than 1. Okay, so here it is. So these are the objectives, couple of objectives. First one, we need to explain or actually prove how integers are represented using base B, where B is any integer such that B is bigger than. Second objective is to apply the theory of congruences to derive or again prove some divisibility of integers by 2, 4, 8, and so on, and 2 to the k, or any power k, then 5 and powers of 5. Then we're going to look at the 3, we're going to look at 9, we're going to look at 11, we're going to look at 7, we're going to look at 13, and there are many others actually. Even there are more than enough in here. I'm actually presenting more, divisibility tests. Some of these divisibility tests, probably you have used in grade school, and some of them you're familiar with, maybe others you're not. But so we can actually prove why these actually divisibility, tests work. The idea is to actually show a given number is divisible by one of these without carrying out basically the division. Basically, that's the idea. And of course, we want to do this one in a simple way. All right, so let's get started with the first objective. is we want to show that any integer can be expressed as, like in the decimal system, as sums of multiples of digits by powers of p. All right? So here is the first term that we're going to actually prove. Okay, this is the first term. Let's say let b bigger than 1 be an integer. Then actually this is true for every positive, negative, but for our purposes we're going to show it for every positive integer. And every positive integer n can be written uniquely in this form. Form n is equal a to the k, b to the k, plus a k minus 1, b k minus 1, and so on, plus a1 b plus a sub 0, where a sub I lies between 0 is then or equal to b minus 1 for every I between 0 and k. All right. So this can be done in, and of course, and k itself is bigger than or equal to 0 is an integer. That is the highest exponent in here, and of course, these go from here. One other thing we also prefer that the AK does not equal to 0. All right? Like this, it's like putting zeros in, left of a certain number. Now, once we prove this, then in this case, we express n in base b, sorry, as this. So you write n is equal to ak minus 1. In other words, the string of these digits. Now we're going to put sub b, okay, to indicate which base we are actually expressing n as. All right, so there are two parts to this theorem. One is to be able to write, express any integer, any positive integer n in this form. The second part is to show that this representation is unique. So let's go ahead and actually start with the first part. And the idea is to use the division algorithm repeatedly, like we did with the Euclidean algorithm, except in here we're going to be doing the division not using the remainders at each step, but the quotients. Okay? So we're going to start with, so we are given, here's the proof. So we're going to apply the division algorithm repeatedly. as follows. So we're going to start by writing n as q sub 0 times b. Basically, we're going to divide n by b. So there exists, all right, a unique x sub 0, which is the quotient, plus remainders. I'm going to call them actually a's. Okay, so these are the a's. They're going to appear on the actually the representation. Now, if it happens that q sub 0 is equal to 0, then we are done. Then we remember that also the a sub 0 in here is bigger than or equal to 0, less than actually b, or less than or equal b minus 1. All right? Let's put it that way. So then in this case, actually n is going to be a sub 0, and this is going to actually satisfy the properties for what the representation of n is. It's going to be just one single digit. It could be actually 0 itself, all right? Or it could be any number from those digits, which is less than or equal b minus 1. If not, if the q sub 0 does not equal to 0, then we take the q sub 0 and we say q sub 0. We're going to divide it by b again. So we're going to get the q sub 0 is equal q sub 1 b plus a1, where the a1 again is going to be bigger than or equal to 0, less than or equal to b minus 1, because we are dividing by b minus 1. And one other thing, you will notice that the q sub 0 is going to be actually bigger than the q1. All right? Now, we of course proceeded to the second step because the q sub 0 is bigger actually than, sorry, this one is, it does not equal to 0, but this one is actually bigger than or equal to 0 itself. All right, again, if the q1 happens to be equal to 0, then, all right, if the q1 is equal to 0, we stop. And now n becomes equal to, what we're going to do, we're going to substitute for q sub 0 by a1, because this is equal to 0, and back in here, so we get this is equal, let me write it down, q sub 0, b plus a sub 0, and by substituting for q sub 0 by a1, okay, so it becomes a1 b plus a sub 0. And again, we have the a1 actually could be bigger than or equal to 0, but because of actually q1, let me leave this one as q sub 0. Let me see in here. So if the q sub 0 does not equal to 0, then a1 is not going to equal to 0, right? Okay, so a1 does not equal to 0 since q sub 0 does not equal to 0. All right? Of course, this is not a very interesting thing. I mean, we really wanted to assume that we can continue this process, and we're going to show that it must end. All right? So let me write, that we continue this process. So we continue. This process. And obtain these equations. We write them down. So start from the very top. First one, which was q sub 0. Actually, n. We start with n equal to q sub 0b plus a1. And again, a1 is now equal to b minus 1. Then we have the q sub 0 is equal to q1b plus a2. Satisfy this. And we put another one in here. The q2 is going to be actually q1. All right, it's going to be b q sub 2b plus a. Let me see in here. How about if I call this is actually a sub 0? Let me call this is a sub 0. Sorry, this is a sub 0. So we're going to have matching in here with the q's, and this is a1. And then we have a q2 and a2. All right, and so continue and assume that there's, the step before last step where this is k minus 2 is equal a k minus 1 b plus a k minus 1. All right, and still we have here 0 less than or equal a k minus 1 less than b minus 1. And the next one, when we write k minus 1, we're going to see this is equal 0b, and we're going to explain why we get, we must reach 0. And this becomes a k. All right, 0 less than a k less than. Now, we of course reach 0 when we are dividing. The bk minus 1 becomes smaller than actually b. So when we do the division, we're going to come up with 0, and we end up with just the b remaining. All right. Now, throughout this, remember that we started with q0. Okay, and then we continue to the next step. If this is not equal to 0, so we do have a q1, then a q2, and so on. Then we have a q. Actually, this is supposed to be in here, supposed to be the qk. Then we get to the qk. We actually put this is minus 1, then bigger than the qk, which is equal to 0. All right? Now, the reason, actually this must stop because as you see, this is a decreasing sequence of positive integers, okay? And it cannot continue. In fact, at most, there will be q sub 0 steps. So here is at most, we will have the q sub 0 steps. All right. Now, once this stops, then I claim that what we're going to do, we're going to start actually substituting, all right? So we start with n is equal b q sub 0 plus a sub 0. Then we're going to substitute for the q sub 0 by what it is equal to. It's unlike the division algorithm where we started with, the Euclidean algorithm. Sorry, we started from the bottom up. here we start from the top bottom. So we're going to substitute for the Q sub 0 by Q1 B plus A1. And when I arrange this, it becomes actually B squared, Q1 plus A1B. Then I'm going to substitute for Q1. We do one more time. So this becomes the B squared. And the Q1 is a Q2 B plus A2. All right, let's multiply. So this becomes B to the third, the Q2 plus A2B squared. So as you can see, we start getting, the A's with, let me see if I got everything in here. So we get this one. Okay, so this is this, and we have this one. Now we also have this other term in here. We need to have that written there. Let me actually, okay, so this one is, this is for the Q1, okay? All right, but then we have A1B plus A1B. Okay, we have more space in here. So, and that in itself is equal to, right, remember this is all equal N. And then we have the Q2 B to the third plus A2B squared plus A1B. And now we're going to substitute for Q2. All right. I don't want to continue forever, but this one is going to be, the Q2 is PQ3, all right, plus A3. And plus the steps already we have. And now we're going to pick the A3, A sub 3B to the third. And this will actually continue. So we have B to the 4, the Q to the third, plus A sub 3B to the third, plus A2B squared plus A1. All right, so we will continue this, and at the very end, we will get to the A to the K, and this is the final results that we get. So at the very end, we continue doing this, and we find this is A to the K, B to the K, plus A K minus 1, B K minus 1. K1, B plus A. All right. The reason that A sub K does not equal to 0, okay? A sub K does not equal to 0 since actually Q sub K does not equal to K minus 1, sorry, K minus 1 does not equal to 0. Because from the last equation which we have in this list, it was Q K minus 1. That's when I go and divide. When this is not equal to 0, then I go from the previous step, which is Q K minus 2, to this. And then we found this plus A sub K. So this does not equal to 0, and this must not equal to 0 itself. All right, so this proves the actually the representation now we need to prove the uniqueness. All right. So we're going to assume that n can be written in two different ways. And then show they must be equal to each other, of course. And what's equal is the coefficients of the powers of b's. Okay, so to prove the so we're going to assume that n is equal a to the k, b to the k, plus a k minus 1, k minus 1, up to a 1 b plus a sub 0. Also, we're going to assume that n is equal to c. Now, here, if we have to, we can assume some of the c's or right equal to 0. So we're going to make the length of the expansion of n using the a's or the c's is the same. Well, at the end, we're going to find that they must be the same. Okay, all of them. But just in case, being why we could take both of these to have the same number of terms, okay? We have c, k minus 1, and so on. C1, b plus c sub 0. So these both equal to each other, then I can actually set these equal to each other and subtract, so you get subtract them out, term by term. A k minus 1 minus c k minus 1 b k minus 1 and so on. And then we have b times a1 minus c1 plus finally a sub 0 minus c sub 0, and this is equal to 0. So this sum is equal to 0. Now, if it happens that all of f, we have a sub I minus c sub I is equal to 0 for every I between 0 and k, then we are done. Means they are the two representations the same. So let's assume no, it is not. Okay? So by contradiction, otherwise, I don't know if you want to call it contradiction, assume that a sub I minus b sub I does not equal to 0 for some I. Okay? And the I again between 0 and k. We're going to take actually the smallest. Since we are assuming this does not equal to 0, let j be the smallest integer such that between 0 and k, such that c sub j minus, let me say it's a sub j, this is not b, so this is c, sorry, c sub r, okay? All right, so assume that this is for some I, okay, so we're going to take the smallest, we're going to call it a sub j minus c sub j, this does not equal to 0. So starting from the right, okay, if this happens to be, okay, not equal to 0, then our j is equal to 0. If this is equal to 0, we move to the next one, and so on. So we're assuming that one of them must not equal to 0. All right? What does this mean? This means when I write actually this expression by removing all those that are 0, so we end up with removing some of these terms, okay? And I end up with the following. So from this equation, we have the AK minus CK. It could be the last one, but let's assume it, not to be, sort of, okay? And then we have AK minus 1, CK minus 1, BK minus 1, and so on. So the last one, the one which is not equal to 0 is this AJ minus CJ. B, as you see, the index of the coefficient matches with the index of the powers, okay? Because all others from the J plus 1 up is actually all equal to 0. Or actually they decrease, sorry. They're going to be decreasing, J minus 1. All right, so we can factor a B sub J from all of this, and we end up with a K minus CK, B K minus J, and the next one is A K minus 1, CK minus 1, and this becomes B K minus J minus 1, and so on. The very, very, very last term is just going to be the index. I mean, the B is factored out, so it's going to be A sub J minus C sub J. All right? So this is equal to 0. All right, what does this mean? This means that if I remove all those terms, so I'm going to be removing all these terms, all right, actually take them to the other side of the equation. So I end up with A sub J minus C sub J is equal to the negative of this. So what I'm going to do, I'm going to switch the A's and the C's in here. So I get B to the J multiplied by CK minus AK. B to the K minus J, and so on. The next step is CK minus 1, AK minus 1, BK minus J minus 1, and so on. And the very last term in here is going to be CK, let me see what it is going to be in here. Yeah, it will be the J plus 1, right? So it will be the J plus 1 minus AK plus J plus 1. And this one is not going to have any actually B's in it, okay? So this one is going to have just a B. Okay? All right. Yeah, I actually did multiply by, yeah, in here I could actually divide because this is equal to 0. Let me divide actually by this B sub J. So I'm going to divide. And remember that the B is bigger than 1, so we have this. I don't need the B sub J. All right? So this is B. Now, each one of these actually has a B in it, right? Okay, the very, very last one is B, and this one has bigger exponent. So this implies that B divides A sub J minus C sub J. All right? And as a result, this implies that actually So this is going to be a multiple of B, so this is going to be bigger than A sub j minus C sub j is going to be bigger than or equal to B. All right? On the other hand, we want to look at this, both of these, A sub j and C sub j. Let me actually write them individually. A sub j is going to be between 0 and this is less than actually B, right? Or less than or equal to B minus 1. And then we have also the C sub j. And I want to multiply this one by a negative 1. Okay? So I obtain these two inequalities. Then A sub j less than B. And this, because we are multiplying by a negative, so it's going to switch. So the B is going to become in here. All right, negative B, sorry. Less than or equal minus C sub j. And this less than or equal to 0. All right. Now I'm going to add these two inequalities. Now I'm going to get negative B. Actually, because we have less than in here, less than. So it's going to be less than A sub j minus C sub j less than B. All right. Well, let's look at these two statements in here. So we have this one, this inequality, and this inequality. It says that A sub j minus C sub j is bigger than or equal to B, and also it is less than B. Well, this is forces the A sub j minus C sub j to equal to 0. Well, this is a contradiction, okay? This is a contradiction, what we assume that there's. So the question then, why we arrived at this contradiction? Because we assume that is actually there is a, two of these not equal to each other. So hence, we must have the AI is equal to CI for every I between 0 and K. All right? So this proves actually the uniqueness. All right. As a corollary to this, when you look at the binary representation where we use only zeros and ones, so in a binary representation, if you write an integer, positive integer, all right, you write this in a binary system that is base 2. Remember the A's sub I is going to be either 0 or 1. So if I take an n and write it like this, and have A to the K, then 2 to the K plus AK minus 1, 2 to the K minus 1, and so on. Those A's that are 0, we can drop them, okay? And the one which have 1 is going to leave us with powers of 2, right? So this implies that we have this corollary which says that every positive integer n can be written as the sum of powers of 2. Because in here, either the AI is equal to 0 or 1. If it is equal to 0, okay, then we drop of that, and if this means this is equal to 1, so we end up with only adding, all right, the non-zero coefficient terms, and this is exactly what this corollary said. And we did use this in this fast exponentiation. Remember that we said that every integer can be written as a sum of powers of 2. Okay, so this is the basis for that, and we do this squaring, all right, which is successive square. All right, the next objective is to develop some, divisibility test, and I want to start. Probably, most likely, for sure, you are familiar with divisibility by 2. Means if the first, which is the units digit, is divisible by 2, which means it's going to be 0, 2, 4, 6, or 8, all right? And a number is divisible by 4 if actually the first 2 digits, okay, the units and the tenth actually is divisible by 4. And you can actually look at 8 and almost all powers of 2. So we want to prove this is in general, all right, for powers of 2. And I want to state this theorem, state it as a theorem, all right. So this is a divisibility test, divisibility by 2 to the k for k bigger than or equal to 1. So it covers all possibilities. 2 if k is equal to 1, 4 if k is 2, and with k equal to 3, this is 8, and so on. All right? So it says that an integer n, of course, everything here, the n is in decimal. In fact, these divisibility tests depends on what base you're using. You could prove for every base, something equivalent to these divisibility tests, okay? But for our purposes, since we use the decimal system, regularly, we're going to be doing this. All right. So we have an integer n is divisible by 2 to the k for k bigger than or equal to 1 if and only if the number consisting of the last k digits of n is divisible by 2 to the k. Is divisible by 2 to the k. All right, let's look at the proof of this. So let's go this way. Let's assume that two to the k divides the number itself. Then I need to show that if I look at just the last k digits, then that number, this which is a smaller number, all right, is going to be divisible by 2 to the k. So what we're going to do, we're going to write, okay, n as a sum of two numbers, s and k, where s is the first from n to actually k minus 1. So it's going to be a n. That, let's assume actually n is equal to this. Before we do this, let me assume that that n is equal an minus 1, ak minus 1, ak, actually plus 1, then ak minus 1 up to a1, a sub 0. This is base step. All right. Now we're gonna remember that we could write this one as an 10 to the n and so on up to a sub 0. All right. Now we're gonna write n as a sum of s plus capital K, where the s is gonna be this number. Actually, we could use congruences, even divisibility, to derive these divisibility actually tests. All right, so we're gonna, where S is gonna be A sub n to the n plus to the, actually just up to k plus 1. Okay, so a k plus 1, 10 k plus 1, and the k is equal, the a sub k, 10 to the k, and so on up to a1 times 10 plus a sub. All right. So the next thing is, remember that actually we have the 10, because all these are powers of 10, right? So we have, since 10, remember this is actually to the j, is equal to multiplied by 5 to the j, which is equal to the j times 5 to the j. And this is congruent to 0 mod 10. And this is for every j from, let me see in here. No, sorry, I want to say this is congruent to 0 mod 2 to the j. And this is for every j between k and l. So now, actually even to k plus 1 in here, k plus 1. So this implies that if I multiply, this is by a to the j, 10 to the j, this is going to be congruent to, divide this by 0, okay, so it becomes 0 mod 2 to the j. So in other words, every term in S is going to be congruent to 0, and then we can add these, we can apply the properties of congruences. J equal, actually, start from k plus 1 to n, a sub j, and 10 to the j. This is congruent to 0 mod 2 to the j. Right? Which means just 2 to the j, this implies that 2 to the j actually divides S. And this is again for every j between k plus 1 and n. Actually, I wanted, let's see here, wanted one more in here, A, K, plus, actually, want to stop here at AK, yeah, because we go to A sub 0, so for the last K term, I'm sorry, this is 10 to the K. All right, and this actually starts from K minus 1. All right, so there are in here, these are the K last K terms. And in here, these are the first N minus K terms. Sorry. Or just adjustment in here, this goes from K, we just need these to start for every J, B, K, and N, and this is for every this. Now, of course, you are interested in particular, we have 2 to the K divides S. Now, let's look at what we have. We put these together. Remember that we wrote N. We have N is equal S plus K. We are given, our assumption is 2 to the K divides N. And we have shown 2 to the K divides S, so it divides a combination of these, and the combination of these, it's going to be 2 to the K divides actually N minus S. But this is equal to K. All right, so if 2 to the K divides N, then 2 to the K divides the last K digits, all right, of the number. Now let's go the other way around. And in fact, we already have all the pieces that we need. Okay, so let's assume, going this way, assume that 2 to the K divides K. Now we need to show 2 to the K divides N. Again, from the first part, we have 2 to the K divides S, regardless of anything, because this is independent of because all powers, the S has powers of 10s, okay? Now, also we have, since by assumption, two to the K divides K, then it divides linear combination of these, and the linear combination is going to be just adding them up. Divides S plus K, and this is equal to N. All right? Similarly, we can state a same theorem for divisibility by powers of 5. Remember this 10, when we wrote it as 2 multiplied by 5, we took here the advantage of the 2, being, or powers of 2 divisible by all the terms in S. So here's another theorem. All right, let N be a positive integer. Then n is divisible by 5 to the k bigger than or equal to 1, if and only if 5 to the k is divisible by the last k digits of n. So in other words, this is going to be divisible by the a sub k minus 1 n k minus 1 up to a1 times n plus a sub 0. These are actually k terms, all right? So these are last k terms. Because we go to a sub 0, all right? So we have started at k minus 1, so we have k term. So this is what it is, and the proof is exactly the same, except changing from 2 to 5, all right? The next divisibility test that I want to look at is 3 and 9. And this is slightly different the way it works. Here we're going to look at the sum of the digits. So actually this is one of the theorems in the book, theorem 4.5. Is like this, first part, a positive integer n is divisible by 3 if and only 3 is divisible by the sum of all digits of n. And of course the idea here is if the sum of the digits is big itself, you could repeat this process over and over and over again, okay, till you get a number that is actually big, less than or equal to 3, all right? Same thing for 9, n is divisible by 9 if and only if 9 is divisible by the sum of the digits. Of course, of n. The proof of this is actually very straightforward. And we're going to use this idea. We're going to let n equal a sub n, then to the n, and so on, times 10 plus a sub 0. We're going to define f of x, a polynomial with the same coefficients as the coefficients of n. Okay, so this is an xn plus an minus 1, xn minus 1, and so on. Sub 0. All right, where all the a's are the same, so these are actually integers. All right, now we put that n is really nothing but the value of this function at 10. All right. Now let's look at this congruence between 10 and 1. It is congruent mod 3, and mod 9. And for each one of these, we will actually prove the test. Okay? So we have 10 is congruent to 1 mod 3. Now, by the properties that we have shown, this implies that f of 10 is congruent to f of 1 mod 3. But f of 10 is n itself, is congruent. F of 1, if you substitute for x by 1 in here, you're going to come up with the sum of the digits, right? And this is mod 3. Now remember that when two numbers are congruent to each other, mod a certain number, then they leave the same remainder, all right, when divided by 3. Now let's see, assume that we have, assume that the 3 divides n, all right? This implies that n is congruent to 0 mod 3. But since n is congruent to this, mod 3, this implies that an, again, the transitive property, n is congruent to if n congruent to 0 mod n, then it would have that same thing. That means that the remainder, when we divide, okay, n by 3, it's going to be 0. And since this is congruent to n, it must leave the same remainder. So this implies that this is also congruent to 0 mod 3. So it divides. So this implies 3 divides an, which is the sum of the digits. Conversely, if actually this number divides to 3, means that this one is going to be congruent to 0 mod 3, and similarly the n is going to be congruent to 0 mod 3. For the 9, the proof goes like this. We have 10 is congruent to 1 mod 9 also. And then by applying here, instead of using the 3, we use 9 all the way, and we get it for 9. All right. Now let's look at divisibility test for 11. All right. Again, we're going to be using the same idea, using this function. We're applying it to a different congruence relation. All right. So this is theorem 4.6. N is divisible by 11 if and only if 11 is divisible by t, where t equal to is the sum of the digits using alternating sign. So we start with a sub 0 minus a sub 1 plus a sub 2 and so on. This minus. And the last one is going to be minus to the end, where this is the first digit to the left of a n. All right? Okay, so the proof here, again, very simple. We have 10 is congruent to -1 mod 11, right? So we're going to apply that function, okay, the same function. This implies the f of 10 is going to be congruent to f of -1 mod 11. But this one gives me n, and when you substitute by, remember f of x is equal an xn, an minus 1, xn minus 1, and so on. a1x plus a0. So if you put f of -1, it's going to be an minus 1 to the n plus minus 1 to, an minus 1 minus 1 to the n minus 1, and so on. And the last 2 is going to be a1 minus 1 plus a sub 0. So as you see, when we go from right to left, you see that those digits, all right, or the signs are going to be alternating. If it happens that some of these a's is going to be 0, you're going to count it. Means you have to count that is positive or negative. Okay, it's not going to affect the sum, but it needs to be counted. Now, so in other words, this is going to be actually the a sub 0 minus a sub 1 and so on up to minus 1 to the n, an. And this is mod 11. Now, once again, if these two numbers are congruent mod 11, they leave the same remainder. So if n is divisible, means leave the remainder of 0, then this one will actually leave the remainder of 0, means it's divisible, and vice versa. All right? Here's a divisibility test for 7 and 13. Okay? And also actually another divisibility test for 11. But this one is much better than the one I will state, but welcome to use. But it uses the same idea of proof for the 7 and 13. All right, here's the theorem. Let's assume that let n equal an minus 1 up to a1 a sub 0. This is base step. All right? This is an integer, a positive integer. Then, first, 7 divides n if and only if 7 divides, you take the an minus 1 up to a1. All right? You take this number from n by cutting the units and then subtract it out. It was. All right? So the idea here is you take a number and then you start reducing it. Okay, that's the idea. And then you keep repeating this over and over again. I will be looking at an example for this. Then we have, second one is 13. Is divisible by n if and only if 13 is divisible by something similar but different combination. So this is a1 10 minus 9 a sub 0. Also, you can do another divisibility test for 11. If and only if 11 is divisible by an minus 1 up to a1 10. This one minus a sub 0. So you don't take very much. All right? All right. Let's actually look at an example before we do the proof in here. For, let's take n equal equal 2, 4, 8, 1. So what we're going to do is we are saying that 7 is divisible by 2, 4, 8, 1 if and only if 7 is divisible by taking the the first 3 digits, okay, 2, 4, 8, and subtract twice 1, which means subtract just 2. And this is if and only if 7 divides, when you subtract 2 from this, you come up with 246, not very much. But now you can apply it again. So this is if and only if 7 divides 24 minus 2 times 6, which is 12. And this is if and only if 7 divides 12. And you know this doesn't work. So since 7 does not divide 12, this means 7 does not divide that big number. Okay? 2, 4, 8, 1. If you look at 13, similar. Here let me take something I told you that works. So 13 divides 1, 2, 9, 8, 7. If and only if 13 divides 1, 2, 9, 8, minus 63, because the a sub 0 is 7, you multiply by 9. So when you subtract this one out, you come up with 1,235. And again, you apply it. So divide 123 minus 45. That's not bad. And this is equal to 78. Now, 13 actually does divide 78. It does divide because 78 is equal 13 multiplied by 6. So yes, then 13 divides this big number. Well, I can do for 11 an example. Now, the proof of this is again based on finding a congruence relation that is satisfied and get it to work for the number and whatever we're proposing or simplifying. All right. So here is the idea. Again, let's so we have n. The original number goes from this up to a sub 0. We get a little n equal an minus 1 up to a1. Remove the a sub 0. All right? Now, I know that the n, which is equal an 10 to the n, when we expand this, plus a1 10 times a plus 0. If I take a common factor of 10 from this, then I end up with an minus 1, 10n minus 1, and so on, plus a1, okay, plus a sub 0. Now this is actually the little n, all right? So this is little n. So in other words, the n, the number can be written as 10 little n plus a sub 0. All right? Now let's look at some divisibility. Or from this, actually I can multiply this is by 2. So I want to multiply this is by 2. And we get 2n equal to 20 little n plus 2a sub 0. Because I need this 2 sub 0. Now I want to rewrite this. I want to multiply it actually by a negative. Okay? So I get negative 2n is equal negative 2a sub 0 minus 20n. Okay, so we're going to keep this. Yeah. Now we have this congruent. 1 is congruent to negative 20 mod 7. Because this gives you actually 21. All right, that's why we took the negative there. So we have this. All right, now I'm going to multiply this by n. Okay, so I'm going to multiply this congruence by n. We get n is congruent minus the 20n mod 7. So I can replace in this negative 2n, all right, we're going to make it a congruence now. We're going to replace the negative 20n by just n. So this becomes negative 2a sub 0 minus n mod 7. All right? Now, 7 is going to be divisible by negative 2n if and only if, because both of these are congruent to each other, so they're going to leave the same remainder, means divisible or not divisible, okay? If and only if 7 is divisible by negative 2 a sub 0 minus n. But since 7 is relatively prime to 2, so or the negative, we can remove the negative as well. So this implies 7. If 7 is divisible by negative 2n, then 7 is divisible by n, and vice versa. If and only if 7 is divisible by n, actually minus. Let me see in here. We need a plus in here. Where is this thing in here? Yeah, I'm adding, actually, I'm replacing, sorry, the negative 22n, I'm replacing it by plus n. Yeah. Or this is a plus n. Or we could write this one as n minus 2a sub 0. I'm replacing the negative 22 n by n. All right? So this means if and only if this is divisible by it. And this is exactly what we have to show. For the 13th, the same kind of idea, except we have a different congruence in it. Okay? So let me, so all this, what we're going to use, except we're going to have a different, the same congruence, we're going to just multiply, actually a different congruence, okay? So we have, okay, from part A, we have the n is equal 10 little n plus a sub 0, all right? Now this is the congruence that I will actually need in here. So I want to multiply this is by 9. This is 90n plus a sub 0. 9a sub 0. And again, we're going to write this is as negative 9n is equal negative 90n minus 9a sub 0. Now we need to use this. Since 1 is congruent to minus 90 mod 13. All right. Then we can multiply this is by n. So we get n is congruent to minus 90n mod 13. And now we're going to go back to replace that negative 90n by just positive n. So from here and here, all right, we have minus 9n is congruent to n minus 9a sub 0. Now, we have mod 13. Now, we have 13 is divisible by minus 9 if and only if 13 is divisible by n itself. If and only if 13 is divisible by n minus 9a sub 0. Alright, so this is what we needed, and this is it. Alright. There are other applications they have not actually discussed in the book. That is the use of congruencies in doing what is called adding, some digits to, decimal or binary as an error check. Okay, really this is not a very good system, because only it can check for one error, and sometimes even it doesn't. All right, so I don't want to talk about that any more. All right.